Google seems to have an answer. It has unveiled a new chip called Willow. Now, Willow is not like any other chip we know. It's a quantum chip. In simpler words, it can solve a problem that none of our supercomputers can.
The astrophysicist Neil deGrasse Tyson has spoken. What to believe, what to uphold in the field of physics. Is science suffering from inconsistencies because of the arrival of smarter artificial intelligence tools? Today, it might be hard to believe that a theory worth 1 million years to prove is only analyzed in seconds through a quantum chip. Has Einstein made a huge mistake all this time? Renowned astrophysicist Neil deGrasse Tyson has consistently emphasized the importance of scientific theories, stating relativity, gravity, quantum, electrodynamics, evolution. Each of these theories is true, whether or not you believe in them. This perspective underscores his respect for established scientific principles, including Einstein's theories of relativity. Regarding a recent announcement of the quantum chip, Tyson acknowledged its potential, but also highlighted the necessity of practical applications. In a Q&A, he noted that while such computational power is impressive, its true value will be realized when it addresses real-world problems. Tyson has also expressed admiration for Einstein's contributions to physics, particularly his work on stimulated emission, which laid the groundwork for technologies like lasers. He has referred to this equation as his favorite of Einstein's, emphasizing its profound impact on modern technology. Tyson maintains a balanced view, acknowledging the advancements brought by quantum computing while upholding the enduring relevance of Einstein's theories in explaining the universe's fundamental workings. But let's go back to the quantum chip Tyson has acknowledged. Meet Willow. In December 2024, Google unveiled a groundbreaking new quantum computing chip named Willow. This announcement made headlines worldwide, not just because of the chip's impressive capabilities, but because it marks a significant leap forward in the quest to unlock the full potential of quantum computing. Developed by Google's quantum AI team, Willow isn't just an incremental improvement on past technology, it represents a major milestone in solving complex problems that were once considered unsolvable by classical computers. With Willow's introduction, we are seeing the beginning of a new era in computing, one that has the potential to revolutionize industries, ranging from healthcare to energy. As quantum computing becomes more practical and accessible, Willow is positioned to play a key role in that transformation, pushing the boundaries of what computers can do. At its core, Willow is a 105-qubit superconducting quantum processor, and it's built to harness the principles of quantum mechanics to solve problems much faster than traditional computers ever could. For some context, in classical computing, information is represented as bits, which can either be a 0 or a 1, but in quantum computing, qubits can exist in a superposition, meaning they can represent 0, 1, or both at the same time. This ability to process multiple possibilities simultaneously enables quantum computers to perform certain tasks exponentially faster than their classical counterparts. Willow, specifically, takes advantage of quantum phenomena like entanglement, where qubits that are entangled influence each other's states, even when separated by vast distances. This is an incredibly powerful property that allows for parallel processing at an unprecedented scale. In short, Willow is not just another chip, it's a sophisticated quantum machine capable of performing calculations far beyond the reach of traditional supercomputers. So far, so excellent exponential error reduction. One of the major hurdles in quantum computing is the issue of quantum errors. Qubits are highly sensitive to their environment, meaning they are prone to errors caused by external influences like temperature fluctuations, vibrations, or electromagnetic radiation. Historically, as the number of qubits in a system increased, so did the frequency of errors, making computations unreliable. Willow has tackled this issue head-on by demonstrating exponential error reduction. In simple terms, this means that as more qubits are added to the system, the error rate actually decreases, something that had been widely considered unattainable before. This achievement is crucial because it moves quantum computers closer to performing reliable, error-free calculations on a large scale. In fact, this below-threshold performance could allow Willow to scale up without the usual risk of instability, paving the way for more complex and meaningful computations in the future. Unprecedented computational speed. When it comes to computational speed, Willow has set a new benchmark. The chip was able to complete a benchmark computation in just 5 minutes, a task that would take even the most powerful classical supercomputers about 10 septillion years to complete. The mind-boggling difference in time is a testament to the raw power of quantum computation. While this speed is currently applied to very specific problems, it hints at the vast potential quantum computers have for solving real-world issues. From optimizing drug discovery to enhancing financial modeling, quantum computing could ultimately accelerate advancements in fields that rely heavily on processing large sets of data. Willow's computational capabilities could open up new doors for scientific simulations, artificial intelligence, and even cryptography, all areas where speed and accuracy are of utmost importance. Real-time error correction. One of the most critical aspects of any computing system is its ability to maintain accuracy and integrity during operations, especially as the complexity of tasks increases. Willow excels in this regard, as it incorporates real-time error correction. This feature allows the system to detect and correct errors as they occur, ensuring that computations remain reliable, even under challenging conditions. In traditional computing, error correction is generally performed after a computation is completed, but with quantum computing, this process becomes even more crucial. Without real-time error correction, quantum systems would produce unreliable results due to the inherent instability of qubits. Willow's integration of this technique represents a pivotal development that will make it possible for quantum computers to handle larger-scale problems without compromising their performance or accuracy. This chip implications. The introduction of Willow has huge implications for a variety of sectors, ranging from healthcare and energy to artificial intelligence and material science. For example, in drug discovery, quantum computers like Willow have the potential to simulate molecular interactions with far greater accuracy than traditional computers. This could dramatically speed up the process of designing new medications or vaccines. Similarly, in the field of battery design, quantum computing could help scientists model materials at the atomic level, leading to more efficient and long-lasting batteries, key for the future of electric vehicles and renewable energy. Another exciting possibility lies in fusion energy. Quantum simulations could help scientists design better reactors by optimizing reactions at the quantum level, potentially providing us with clean, unlimited energy. However, despite these enormous potential benefits, we are still in the early stages of quantum computing development. While Willow's performance is groundbreaking, it's unlikely that commercial applications of quantum computing will be widespread until at least 2030. Developing practical quantum technologies for everyday use requires overcoming significant hurdles, including scalability, reliability, and affordability. Google's Willow quantum chip is an exciting step toward making quantum computing a reality. With its capabilities to reduce errors, increase computational speed, and implement real-time error correction, Willow is positioning itself as a trailblazer in the quantum revolution. While it's still early in the journey, Willow's development marks a critical point of transition from theoretical research to practical, real-world applications. However, even with these advancements, there's still a lot to be done before quantum computing can become part of mainstream technology. We're looking at a future where quantum computing could disrupt industries, solve complex problems, and create new breakthroughs in fields ranging from medicine to energy. In the meantime, Willow's achievement is a sign that the quantum era is closer than ever before, and we can expect to see even more exciting advancements in the years ahead. A quantum leap or a challenge to the past? Willow has generated a lot of buzz in the tech and scientific communities, but beyond the immediate implications for computing, there's also a larger question. How does Willow, with its extraordinary quantum capabilities, relate to some of the most fundamental theories of physics, especially those proposed by Albert Einstein? Known for his work on relativity and quantum theory, Einstein's ideas have been foundational in shaping modern physics. Yet, as quantum computing evolves, it challenges the very principles Einstein built his theories upon. So, is Willow's arrival a revolutionary step forward that leaves Einstein's theories behind, or is it merely an extension of his work in a new domain? The Einstein legacy. Einstein's theories of relativity, especially general relativity, revolutionized our understanding of space, time, and gravity. General relativity, which describes how objects with mass distort space-time, has been confirmed in numerous experiments and is fundamental to everything from GPS satellites to our understanding of black holes. On the other hand, quantum mechanics, the field that governs the behavior of particles on a tiny scale, also owes much of its early development to Einstein, especially through his work on the electric effect, which won him the Nobel Prize in Physics in 1921. However, despite his contributions to quantum theory, Einstein never fully embraced it. He famously said, "God does not play dice with the universe," reflecting his discomfort with the inherent randomness and uncertainty that quantum mechanics seem to suggest. While quantum mechanics describes the behavior of particles in probabilistic terms, Einstein believed in a deterministic universe. So, when it comes to Willow and its quantum computing power, it raises an interesting question. Can quantum computing's unpredictability and complexity really coexist with Einstein's deterministic view of the universe? What has changed? Willow's quantum computing abilities are built on principles directly derived from quantum mechanics. As a quantum processor, Willow uses qubits, which, unlike traditional bits that are either 0 or 1, can exist in multiple states at once due to superposition. This ability enables Willow to perform calculations that classical computers would take thousands of years to complete in a fraction of the time. But how does this square with Einstein's views? Einstein's theory of relativity works beautifully on macroscopic scales. Think of planets, galaxies, and black holes. But when we zoom in on the atomic and subatomic worlds, relativity falls short. That's where quantum mechanics steps in, with its strange and non-intuitive behaviors like entanglement, where particles remain connected no matter how far apart they are, and superposition. These concepts don't align with Einstein's worldview, which was based on the idea of local realism, the notion that objects have definite properties and exist in a specific place and time, regardless of observation. Quantum computing, and Willow in particular, thrives in this weird, non-local quantum world, where particles can be in multiple places or states at the same time. This directly challenges the deterministic, predictable model of the universe that Einstein championed. While quantum mechanics doesn't prove Einstein wrong, it does suggest that there's more to reality than meets the eye, a reality that doesn't always follow the smooth, orderly patterns Einstein envisioned. Can they coexist? One of the most fascinating and sometimes controversial aspects of Willow's quantum computing power is its use of quantum entanglement. In essence, entanglement means that particles can become interconnected in such a way that the state of one instantly influences the state of another, even if they are separated by vast distances. This phenomenon defies the limitations of classical physics and challenged Einstein's idea of spooky action at a distance. Einstein was initially skeptical of entanglement, dismissing it as an illusion and a contradiction to his own theories. He believed that information about the state of an object should be local and finite, which would prevent any instantaneous action between distant objects. But experiments have since confirmed entanglement, showing that particles can indeed be linked in ways that transcend distance and time. For Willow, entanglement plays a key role. As a quantum chip, it relies on the entanglement of qubits to perform complex calculations. This is where Willow might seem to diverge from Einstein's theories, especially his understanding of how the universe should behave at its most fundamental level. But rather than disproving Einstein's theories, Willow's ability to harness quantum entanglement demonstrates that, while Einstein's theories work perfectly on a larger cosmic scale, they may not capture all the subtleties of the subatomic world. Quantum mechanics and relativity may simply operate in different realms, each governing different aspects of reality. So, where does this leave us with Willow and Einstein? Quantum computing chips like Willow don't prove Einstein wrong, but they do highlight the limits of his theories in explaining the subatomic world. The relationship between quantum mechanics and general relativity remains one of the biggest unsolved mysteries in physics. In fact, physicists are still working to find a way to reconcile the two theories in a unified quantum theory of gravity, something that could potentially bring together the strange world of quantum particles with the grand cosmos described by relativity. Willow, then, could be seen as a step forward in our understanding of the quantum realm, a realm that Einstein himself never fully accepted. Yet, it doesn't invalidate Einstein's theories in the realms where they excel, such as predicting the motion of planets or the behavior of black holes. Quantum mechanics and general relativity operate in different domains, and it's possible that the future of science lies in a theory that can bridge these two, where quantum chips like Willow may play a critical role in unlocking the mysteries of the universe. In the end, Willow doesn't exactly prove Einstein's theories wrong, but it challenges them in profound ways. Quantum computing represents a leap into a new frontier of physics, one that Einstein himself might have found both fascinating and frustrating. As quantum technology continues to evolve, it's likely that it will force us to rethink old paradigms and refine our understanding of the universe. Rather than seeing Willow as a negation of Einstein's work, it's perhaps better to view it as an expansion of what we know, showing that there's still much more to learn about how the universe works, both at the quantum level and on the cosmic scale. The journey from Einstein to Willow might be long, but it's a path that promises to deepen our understanding of the very fabric of reality. Willow disproves Einstein. True or false? The rise of quantum computing, especially demonstrated by Willow, does not disprove Einstein's theories. In fact, general relativity and quantum mechanics operate in separate domains of physics. General relativity describes the large-scale structure of the universe, such as the motion of planets and the behavior of black holes, while quantum mechanics governs the behavior of particles at the microscopic level. These theories have been experimentally validated in their respective domains and remain cornerstones of modern physics. Willow, as a quantum chip, is primarily concerned with the subatomic scale, where quantum mechanics holds sway. The peculiar behaviors of particles, such as superposition and entanglement, simply do not apply at the macroscopic scale that Einstein's theories cover. For instance, the equations of general relativity perfectly describe how the Earth orbits the Sun, how gravitational waves propagate through space, and how massive objects like black holes distort space-time. These phenomena do not rely on quantum behavior and have been confirmed repeatedly in real-world observations. Furthermore, quantum mechanics has not overturned general relativity. Instead, it reveals the limits of classical physics when dealing with the smallest building blocks of matter. For example, quantum mechanics explains the behavior of particles at the atomic and subatomic levels, but it does not yet account for gravity, which remains governed by Einstein's general relativity. This is why scientists are still working toward a unified theory of quantum gravity, a framework that would combine quantum mechanics with general relativity. Willow and other quantum technologies represent a powerful tool in this ongoing effort, but are not evidence against Einstein's work. It is essential to note that while Einstein contributed significantly to the development of quantum theory, he did not fully embrace the quantum world as it was developed by other physicists such as Niels Bohr and Werner Heisenberg. Einstein was uncomfortable with the probabilistic nature of quantum mechanics, as it introduced an element of randomness that contradicted his belief in a deterministic universe. However, modern quantum mechanics has since expanded to include many phenomena that Einstein himself could not have anticipated. With the advent of quantum technologies like Willow, scientists have demonstrated that quantum entanglement and superposition are not just theoretical ideas, but powerful tools that can be harnessed for practical use in computing, cryptography, and other fields. These advancements do not invalidate Einstein's work. They simply extend our understanding of the universe by demonstrating that quantum mechanics and relativity are both necessary for understanding different aspects of reality. Truth be told, Willow and Einstein's theories are not incompatible. While Willow and the quantum world it represents challenge some of Einstein's ideas, they do not prove his theories wrong. Instead, they reveal the limitations of classical physics at the quantum level, where phenomena like entanglement and superposition come into play. Einstein's general relativity remains the best description of large-scale gravitational effects, and his work laid the foundation for much of modern physics, including quantum theory. Quantum computing, represented by Willow, is not an enemy of Einstein's work, but rather a new frontier in physics that operates alongside it, tackling the mysteries of the universe at a scale that Einstein's theories were never designed to explain. Ultimately, Einstein's theories and quantum mechanics each address different aspects of reality, and the challenge now is to reconcile them into a unified theory, something that Willow and future advancements in quantum computing might help us achieve. Aside from quantum chips having potential to disprove Einstein's studies, what else could negate them? Theory remains a theory. Albert Einstein's theory of relativity, particularly his two theories, special relativity, 1905, and general relativity, 1915, revolutionized our understanding of space, time, and gravity. These theories transformed physics, providing a new framework for how we think about the universe. Special relativity showed that time and space are not absolute, and general relativity reshaped our view of gravity, explaining it not as a force, but as the curvature of space-time caused by mass and energy. While these theories have been confirmed through numerous experiments and observations, they are not without their critics. Over the years, some aspects of Einstein's theories have been questioned, challenged, or even outright negated by new developments in physics. Let's take a look at some of the major criticisms and negations of Einstein's theory of relativity. Role of quantum mechanics. One of the most significant critiques of Einstein's theories comes from the realm of quantum mechanics. General relativity and quantum mechanics have been incredibly successful in their respective domains. General relativity describing the large-scale structure of the universe, and quantum mechanics governing the behavior of particles on a tiny scale. However, they are incompatible with one another. General relativity is a smooth, deterministic theory, while quantum mechanics is probabilistic and relies on the idea of uncertainty, as encapsulated by Heisenberg's uncertainty principle. This fundamental divide has left many physicists frustrated, as there's no single theory that successfully combines both frameworks into a unified description of reality. Einstein himself struggled with the quantum realm, famously rejecting the probabilistic nature of quantum mechanics with his remark, "God does not play dice with the universe." This discomfort with quantum mechanics is one of the reasons Einstein resisted certain aspects of the quantum world, particularly phenomena like quantum entanglement, which he called spooky action at a distance. As quantum mechanics has continued to develop, especially with advancements like quantum computing, it has only highlighted the differences between it and general relativity, calling into question whether both can be fully reconciled. The missing quantum theory of gravity. One of the biggest unsolved problems in physics today is the lack of a quantum theory of gravity. Einstein's theory of general relativity works remarkably well on large scales, explaining phenomena like black holes, gravitational waves, and the expansion of the universe. However, it breaks down when trying to explain phenomena at the quantum scale, where the rules of quantum mechanics dominate. This incompatibility means that we cannot yet describe gravity at the quantum level, which is crucial for understanding things like the interior of black holes or the early moments of the universe during the Big Bang. The need for a quantum theory of gravity has led to multiple attempts at unifying general relativity with quantum mechanics, such as theories like string theory and loop quantum gravity. However, none of these have been definitively proven yet. This lack of a unified theory points to the possibility that Einstein's general relativity might not be the final word on the nature of gravity, and there could be deeper, more fundamental laws that remain undiscovered. The dark matter and dark energy conundrum. Einstein's theory of general relativity has been extraordinarily successful in describing how gravity works on cosmic scales. However, when we look at the universe as a whole, there are some glaring inconsistencies that it can't fully explain. One of the most famous examples is dark matter and dark energy. Observations of galaxies and the universe's large-scale structure suggest that most of the universe is made up of dark matter, which doesn't emit light and can't be detected directly, and dark energy, a mysterious force that seems to be driving the accelerated expansion of the universe. Together, these make up about 95% of the universe's energy content, but they do not fit into Einstein's theory. General relativity predicts how gravity should work based on the distribution of visible matter, yet the observed behavior of galaxies and clusters of galaxies suggests there is something invisible, dark matter, exerting gravitational influence. Furthermore, Einstein's equations were modified by the introduction of the cosmological constant, which he initially called the greatest blunder of his life, to account for the accelerated expansion of the universe. This mystery of dark energy points to the idea that our current understanding of gravity might need a major overhaul to account for these unseen components of the universe. Gravitational singularities and nature of black holes. Another significant criticism of Einstein's theory concerns the concept of gravitational singularities, particularly at the center of black holes. According to general relativity, when a massive star collapses under its own gravity, it can form a singularity, a point where space-time curves infinitely, and the laws of physics as we know them break down. However, the idea of a singularity, where physical quantities like density and temperature become infinite, is deeply troubling and suggests that our understanding of gravity is incomplete. Theoretical physicists have long recognized that the singularity problem points to the need for a quantum theory of gravity. In the quantum realm, the very idea of infinite quantities may not even be meaningful. As a result, the presence of singularities in general relativity has led some physicists to believe that Einstein's theory might not fully capture the true nature of black holes or other extreme conditions in the universe. New theories like quantum gravity and loop quantum cosmology suggest that the true nature of singularities might involve a more complex quantum behavior that Einstein's theory does not account for. Limitations of the Big Bang's model. While Einstein's theories have been instrumental in shaping our understanding of the universe's origin, the Big Bang model itself is still subject to some limitations. General relativity predicts that the universe began as a singularity, but this leads to the same problem mentioned earlier: infinite densities and a breakdown of the laws of physics. This doesn't provide a satisfying answer to the question of why or how the universe began. Some critics of the Big Bang model argue that it might be incomplete, and alternative models, such as the multiverse theory or cyclic models of the universe, are being explored as possibilities that extend beyond Einstein's framework. So, is Albert's theory outdated? In conclusion, Einstein's theory of relativity remains one of the most powerful and influential scientific theories ever devised. It has been confirmed in numerous experiments and observations, and it continues to be a cornerstone of modern physics. However, as we push the boundaries of our understanding with the discovery of dark matter, dark energy, and the ongoing search for a theory of quantum gravity, it becomes clear that general relativity has its limits. Einstein's theories, while revolutionary, may not be the final explanation of the universe's workings, especially when we examine the quantum realm and the extreme conditions of black holes and the early universe. Critics of relativity are not dismissing Einstein's work, but are rather building upon it, trying to uncover a more complete theory that can reconcile the discrepancies between quantum mechanics and general relativity. The future of physics likely lies in a new theory that bridges the gaps, with Einstein's legacy providing a crucial foundation for that journey. The limitless chips. Quantum chips might sound like something out of a sci-fi movie, but they're becoming very real, and fast. As companies like Google, IBM, and others race to build powerful quantum computers, we're starting to get a glimpse of what the future might look like. Unlike classical computers, which rely on binary bits, zeros and ones, quantum computers use qubits, units that can exist in multiple states at once thanks to the wild properties of superposition and entanglement. This gives quantum chips the potential to solve certain problems much faster than even our most advanced supercomputers. In the near future, quantum chips will likely start showing up more in research labs, universities, and eventually in industries like pharmaceuticals, logistics, cybersecurity, and climate modeling. For example, simulating molecules at the quantum level, something classical computers struggle with, could become much easier, leading to faster drug discovery and new materials that were once impossible to create. Quantum chips might also improve how we optimize supply chains, forecast the weather, or secure sensitive data through new forms of quantum encryption. That said, we're not quite at the finish line. While quantum chips like Google's Willow are making headlines, the technology still faces big challenges. Qubits are extremely fragile. They can lose their quantum state due to heat, noise, or even tiny vibrations. This is why researchers are also focused on quantum error correction and building more stable hardware. But as these hurdles get smaller with each breakthrough, we'll see more reliable quantum systems that can be scaled up and used for broader, real-world tasks. Looking further ahead, a fully developed quantum computing era could radically transform how we interact with data. Problems that take thousands of years for a classical computer to solve might only take seconds on a quantum machine. Fields like artificial intelligence, finance, cryptography, and even space exploration could be reshaped. Imagine being able to simulate entire ecosystems, optimize planetary orbits for space missions, or break current encryption systems in seconds, which is why post-quantum encryption is already being developed. In short, the future of quantum chips is incredibly exciting, but also unpredictable. We're still in the early stages, like the 40s and 50s were for classical computing, but the momentum is building. As the technology matures, it will likely bring not just faster computers, but entirely new ways of thinking about problems and possibilities. Whether you're a scientist, a tech lover, or just someone curious about the future, it's safe to say that quantum computing is something worth keeping an eye on. Is super advanced AI taking over the world, even changing history and existing theories? Share your comments below. Thanks for watching the video.